The work energy theorem tells us that the initial energy, which is a number that I can calculate, by calculating the total kinetic energy and different forms of potential energy that a system has, that energy can be changed by work. Positive work adds to that energy, negative work takes away from that energy, and in the end, what I'm left with is the final energy. The idea here, the important idea of the moment, is that work changes energy. In the case of a closed system, all the work does is rearrange the energy, moving it from kinetic to potential. But external work, like the work done by friction, can increase or decrease the energy. Typically, friction decreases the energy. But if I push on a system, lay hands on it, and do positive work, I can increase the energy of the system. So there's a certain accounting in our law of conservation of energy for the change in energy. Just as in the very beginning of our course, we were interested in the change in position, and we discovered that objects in our universe change their positions at different rates. It's also meaningful that when energy changes, we might have some interest in the rate at which the energy changes. Just as we define velocity as the rate of change of position, the change in energy divided by the time in which the energy changes is termed power. Now, power is given a special symbol. It's a script P. I personally don't do a good job of writing a capital cursive P, certainly not one as fancy as this one. So I have a tendency personally in my own handwriting to use a backwards paragraph symbol. I have to distinguish it from a lowercase p, which in our course will be momentum, and from an uppercase p, which is pressure. We don't have any cause to use pressure in our course, but if I'm teaching a course on engineering thermodynamics and I'm trying to design a power plant, I might find myself with power and pressure in the same equations, and so I need some differentiation there. So power is sort of a fancy P, is the rate at which energy changes. So since the energy is measured in joules, and our SI unit for time is the second, then the units that we would use for measuring power would be joules per second, which is otherwise known as a watt. You can see this in everyday life, particularly with regard to light bulbs. You have a light bulb in your house that, let's say, is 60 watts. That means it puts out 60 joules every second of luminous energy. Well, that's not technically true because it also generates quite a bit of thermal energy. The light bulb gets hot. Even you yourself are luminous because although we cannot see you glowing, you emit infrared radiation because you have a metabolism that's releasing chemical potential energy, producing thermal oscillation inside of your body, and you glow. And it turns out that the human being at normal body temperature radiates energy at about 110 watts. So you are very much, in that regard, like a light bulb. This all makes the power a very simple and familiar idea. Just as velocity is the rate at which position changes, and acceleration is the rate at which velocity changes, power is the rate at which energy changes. But as we've studied in this unit, we realize that energy comes in many forms. It's perfectly fine to say that power is the change in energy over time, the rate of change of energy. But I could also describe power as the rate of change of the kinetic energy by calculating the change in kinetic energy divided by time. Kinetic energy measured in joules, and so that would have joules per second as well. So changing the kinetic energy over time is also an expression of power. I could also change potential energy, delta U over delta T. This is also an expression of power. Because energy comes in several forms, power can be calculated in several different ways. The rate of change of kinetic energy might describe the power of an automobile engine. The sole purpose of the automobile engine is to change the velocity of the car and therefore change its kinetic energy. The rate of change of the potential energy as an expression of power might be the power of the motor used to raise an elevator car. And an elevator has to do work to raise the elevator and change the gravitational potential energy of the elevator and its occupants, changing the potential energy over time. All of these are legitimate forms. So when you're solving problems involving power, really what you need to look for is how the energy changes in the time that the energy changes. And then the ratio is simply calculated the power. Of course, energy, kinetic energy and potential energy and the total mechanical energy, not the only quantities that have units of joules. Work, which changes the energy, also has units of joules. When work is done, it transforms the energy, changes the energy. And so work is a certain number of joules of change in and of itself. So another definition that I have for power is the work that is done divided by the time in which that work is done. So here I have the power is equal to the work over the time, but I know that my work, by definition, is the parallel component of the force multiplied by the displacement. So I make that substitution in the numerator and I discover all of a sudden F parallel delta x divided by delta t. Delta x divided by delta t is familiar to me. It is the average velocity by definition. This gives me another tool in problem solving. I realize in a situation where the force is constant that the power can be calculated as the parallel component of the force multiplied by the average speed. You'll find that that's a rather handy tool for solving very specific physics problems like the ones that appear in your homework. One final observation here about units. Power is a very, very important engineering and industrial concept because work needs to get done, often in an engineering context, and a kind of work that needed to be done in the Industrial Revolution in Europe. There's a great need for coal, digging coal up out of the earth. But the trouble is, you would dig up some coal and you dig and dig and dig, and the water table is so high, particularly in areas of Europe, that water would begin to infiltrate into the mine, so you can't get at the coal. So what you had to do was to build a pump. You drill a shaft down into the mine, there'd be a pump there, and the pump would pump water to the surface based on rotation. So on the surface, you would have some horses or oxen, and they would be attached to yokes, and they would walk around in a circle, rotating the pump shaft, producing doing the work to raise the gravitational potential energy of the water out of the mine so that you could get at the coal. So early in the Industrial Revolution, the work that needed to be done was done often by horses. But of course, with the advent of the steam engine, there became a new and much more powerful way to get the work done. So imagine you're a salesman of steam engines and you come and you tell someone, look, we can have this steam engine and do all this. And the person says, well, I already have these horses. And you might say, well, look, this engine that I have here is 12 horsepower. It can do the work of 12 horses in the same amount of time, which is the origin of the unit of power known as the horsepower. Horsepower is still something that we talk about today in the context of cars, for example. A car has a certain horsepower, and that's described as a desirable quantity because if the horsepower describes the power describes the engine's ability to change the kinetic energy of the car at a high rate. So horsepower comes up from time to time, and so that unit conversion is handy to have. All you need to remember is that 1 horsepower is about 746 watts of power. And then that will get you through solving some of the problems. Very, very simple. Power, the rate at which work is done.